Okay, in the previous two lectures, I think, video lectures, we analyzed the mapping from S domain to Z domain under this e to power ts transformation. Okay, this mapping is concrete in the sense that it actually happens when we are discretizing a continuous time dynamic system with some sort of sampling involved at the input. Okay, so this is an actual mapping, and we need to analyze from this perspective because we need to understand what happens if we move from continuous domain to discrete domain using a digitization operation. Okay, sometimes you want to go from Z to S domain for analysis and design purposes. Okay, but the problem is this inverse mapping is even more complicated, and it's due to the fact that, as you can remember, okay, for example, if we map imaginary axis, we know that mapping of this region, where this is omega s divided by 2, this is minus omega s divided by 2, equal to this mapping of this region and mapping of this region, because there's a repetition periodicity in this mapping, which makes the analysis and design a little bit more complicated if we want to go from Z to S domain. Okay, why we do that? Because in S domain, in classical control theory, we have many tools that we can analyze systems in terms of stability or other performance metrics such as phase and gain margin. And also, we want to design controllers using the techniques that we already know in S domain. Okay, so we want to do that, but this mapping is kind of not used in the sense, so we use a different mapping called bilinear transformation, which is some sort of a fictitious transformation. Okay, so this is not an exact real transformation. Okay, so we are doing this transformation for mathematical and computational purposes. Okay, so let's move on. Okay, what is this? Okay, actually, the definition of this mapping is quite easy. Okay, so Z is defined as 1 plus t to the power 2 s bar, 1 minus t to the power 2 s bar. Okay, s bar is a fictitious S domain, which has similar characteristic with our S domain, but this is a new domain. So what we do is, so if this is S domain, we move to Z domain, and then we move to S bar domain. Okay, so S to Z, Z to S bar. There are some similarities here, but there are some major differences. Okay, good. So let's change the results. Okay, so let's analyze this mapping. And also, if you want to write S bar is simply is this form. Okay, T is Z minus 1, Z plus 1. Okay, so let's look at the magnitude of Z, which is equal to 1 plus t to the power 2 s bar, 1 minus t to the power 2 s bar. I can write this as, okay, so let's make it easier. 1 plus t to the power 2 s bar. Okay, 1 minus t to the power 2 s bar. Okay, so I wonder what happens if I limit my z to unit circle. Okay, so if magnitude of z is limited inside unit circle, I wonder what kind of constraints I have on S bar domain. Okay, so in that respect, I can easily see that 1 plus t to the power 2 S bar is less than 1 minus t to the power 2 S bar. Okay, if I write S bar as this sigma bar plus j omega bar, this is a fictitious magnitude, this is a fictitious complex frequency. Okay, I can easily see that this is equal to, okay, so if this is true, I can take the squares, right? If this magnitude is less than this magnitude, if I take the squares, I will take obtain the same thing. This is equal to t over 2 sigma bar plus 1 square, t over 2 omega bar square is less than t over 2 sigma bar minus 1 square plus t over 2 omega bar square. As you can see, this will cancel, and it implies that z bar less than 1 is simply equal to, or simply implies that sigma bar is, no, you don't need to say that, is less than 0. Okay, so sigma bar is less than 0 is the only chance that this inequality will hold, because there's plus 1 here, there's minus 1 here. You can look at the detail. Okay, so it is kind of an expected result because, okay, z bar less than 1 means that we are limited to the region inside the unit circle, which is the whole stable region, and sigma bar less than 0 is technically open left half plane. And since S bar is a fictitious continuous time domain Laplace transform expression, and mapping a stable region in Z domain to stable region in S domain is a useful result. Okay, so this is technically the mandatory, but it's really useful. Okay, good. So similarly, Z bar is equal to 1 will simply state that sigma is equal to 0, which means that if we map the unit circle, we will simply obtain the imaginary axis. Okay, so these are good because in this transformation, as you can see, we are just covering the important regions. Of course, we need to look at the frequency, but the core idea is the region stays inside the unit circle, is mapped to all open left half plane, and unit circle is mapped to the imaginary axis. Okay, so this is a more useful transformation with respect to the e to power ts mapping. Okay, this is the more important part about the bilinear transformation, especially if you talk about the midterm tree. I will go into that. But there's a different aspect which will be more important in the following lectures. Okay, good. So this is here. This is the same thing. Okay, which is here. Okay, I'll show you that. Okay, good. So let's go here. Let's open a clean page. Okay, now let's concentrate on Z bar is equal to 1. Okay, so we are on the unit circle. Okay, that's important. So it means that Z is equal to e to the power j omega d, right? So we have a just phase, nothing else. And this omega d, which is the frequency in discrete domain, is equal to from minus pi to pi. Okay, that's good. So S bar in that respect is equal to t to the power 2 e to the power j omega d minus 1 e to the power j omega d plus 1. Okay, so if I simplify this expression, okay, this is equal to j 2 over t sine omega d divided by 1 plus cosine omega d. Okay, if you further simplify it, you will see that this is equal to j 2 over t sine omega d divided by 2 cosine omega d divided by 2. Okay, that's good. So if we further simplify it, omega is equal to simply 2 over 2 times tangent omega d divided by 2. Okay, so omega d is the discrete time frequency measured in radians. Okay, and omega is a fictitious frequency. Okay, so we are mapping a frequency to a different frequency. Okay, so omega d, okay, starts from 0 to goes to pi, okay, or minus pi. So we have negative frequencies but positive frequencies, but let's concentrate on the positive frequencies. Omega bar goes from 0 to infinity. Okay, good. So it's kind of good because in discrete domain, we are limited to frequencies from 0 to pi. Okay, so especially if you are taking digital signal processing course, you should know this very well. Okay, but what we are doing is we are stretching this finite frequency region because it's a discrete, it should be finite. But when we are going to an infinite dimensional space where frequency is limited, which is good that 0 to pi is mapped to 0 to infinity. So what does it mean? It simply means that, okay, so this is the unit circle. This part, so omega d is technically the phase also. So it's phase of the complex number and also discrete time frequency. If we go from 0, not 0, it's 1, 0 phase to here in this direction, what are we going to do is we will go from 0 to infinity in continuous domain. So this is z, this is s bar. So technically the upper part of the unit circle is mapped to the imaginary, positive imaginary axis. Similarly, if we look at the, for example, 0 to minus pi, omega bar will go to 0 to minus pi t. Okay, so we will have a different thing. This will be like that, and this will be like that. Okay, so mapping of the imaginary axis is important, and this is the whole story. Okay, this is the z plane, and this is the s bar plane. Okay, so the blue region is mapped to the blue region. So whole stable region is mapped to the whole stable region. This is good. The unit circle, which is technically all of the marginal stable regions, of course, this has more properties, is mapped to imaginary axis. So we map the marginal stable region to marginal stable region. It's technically a curve. So this mapping is, as you can see, it's a one-to-one and onto mapping as opposed to e to the power ts mapping. So it's kind of unique. We know where to map from one point to the other part, and we can always go back and we will face the same result. So you can go from z to s bar to z, you'll always get the same result. Okay, good. So let's do something else about this frequency, and I will finish the topics. Okay, very good. So there is a different meaning here, and it will be more important in the following lectures, and it's after the midterm 3. Okay, so this is a nonlinear map, right? We are mapping omega d to technically omega. Okay, so what we can do is we can linearize this. Okay, because as you know, when omega d is equal to 0, omega will be equal to 0, which is good. Okay, there when one of them is 0, the other one is 0. So if we try to understand the shape in the local neighborhood of the 0 frequency, okay, when we are low frequencies, the behavior can be important. In that respect, what we do is we linearize this map. Okay, omega bar is approximately equal to d omega bar divided by d omega d evaluated at omega d, which is technically the Taylor series expansion times omega d. If we compute that, it will be equal to 1 over t omega d. Okay, that's good. So what is 1 over t omega d? Okay, it's technically the omega c. So what is omega c? Omega c is the actual frequency. Okay, so since we have a sampling time, okay, in order to map actual frequency to the omega d, we simply use this mapping. Okay, it's kind of simple because we have a sampling time, we have a frequency in the continuous domain, or we have a frequency discrete domain. If we try to look at its counterpart in the digital domain, we just look at this. So in that respect, omega bar is approximately equal to omega c. So technically, the frequency in a bilinear domain is similar to the close to frequency in continuous domain if you choose t as your sampling frequency. Okay, why this will be important? It's because in analysis of a digital, when designing digital compensators, okay, instead of designing the compensators control in Z domain, we will go back to S bar domain. And doing this, it's important to keep track of the frequencies. We will design our lead or lag compensators, just assuming our controller and system is continuous, okay? And then we will go back to the Z domain and implement to our system. And the good thing is it will give exactly the same gain and phase margins. Okay, so this is the whole idea. And I will talk about this frequency-based details later. But for the midterm 2, or for the simple step analysis, this is the whole important point. Okay, so if you map to a Z-domain expression where all of your poles are inside the unit circle, they will map to open left half plane. Okay, so if you have an unstable pole, it will map to right half plane. Okay. If you map a pole on the unit circle, it will map to the imaginary axis. The good thing is, this implies that if I have a Z-domain expression transfer function, okay, I can map my system to S-bar domain using bilinear transformation, apply Root-Hurwitz or similar methods, check the stability, and it will guarantee the stability of the discrete-time systems. Okay, so in that respect, the value of t is just user. It's not important. Just choose any t it will give the same result in terms of absolute stability metric.